Okay, this last component of the demo for the Coriolis configuration is devoted to looking at the file analytical.f. So first let me go in application directory and let's do more of the Coriolis readme.txt. Okay, so in the previous two demo we looked at the cpp.defs.h and the modparams.f. Now before editing the analytical.f, which we'll do in just a second, let's look at this Coriolis cpp.def file, Coriolis cpp.defs.h file. And if we look here, we find that there's a couple of places where we need analytical configuration. One is the grid. Okay, so that's one place. The other one is the initial condition. Then we have the surface momentum flux, the surface temperature flux. So these are 4 places now that we have to provide information. And then there's analytical bottom T-flux. So in total we have 5 places in which we have to provide analytical conditions. And so with this in mind, let's start with the first one. And I'm going to keep this window open. And I'm going to go in another editor window. I'm going to go in the ROM's source code. Source code. And then I'm going to go in the nonlinear directory and open the analytical.f. Analytical.f, and then I'm going to go at the very beginning. Oops, sorry. I'm going to go at the very beginning of the file. So now I'm inside analytical.f. So the first thing that I'm going to search is the Coriolis string. And so you'll find that the first occurrence of the Coriolis string is a block of code that has a variable that has the initialization of a variable called btflx, and in fact this one is the bottom heat flux, and so this is the bottom boundary condition for the tracer and the temperature in this case, and we're just going to set it to 0. We need no geothermal heating. So the first one is done. So then let's go to the next one. Okay, so the next one finally is this part here, which is concerning the size in the dimension of the size of the grid in the x and y direction. In this case, it is 3,000 meters because the model uses the MKS system for the x direction and 3,000 meters for the y direction. Then there's other stuff that is considered grid information, which is f naught, which is the Coriolis parameter, and this case this is equal to 2 pi over 12 hours. And then there's also a depth variable that is initialized, which is the depth of our domain. It's just a very square, doubly periodic domain with constant depth of 300 meters in this case. And then here we have also another parameter called beta, and what beta is actually the gradient of the f parameter as a function of latitude. And that's because, as you know, at the poles the rotation is stronger than at the equator, where the rotation is 0. So if you have very, very large domains, you have to account for the fact that there's a natural gradient in f, and you do that by just defining this beta term. If you did that, then you would be running a simulation so-called in the beta plane approximation. If instead your domain is small enough that you can neglect the gradient of f and you just keep the f constant, that would be the f-plane approximation. Okay, so then we search for the next occurrence, and the next occurrence is initialization of a do loop that initializes the variable h, which is the 2-dimensional array containing the depth of the model grid points, and so we put everything to a constant depth, and so we use the depth variable to do that. Let's type next. Now there's another occurrences of the Coriolis parameter, and this is the initial condition for u, okay, and also the initial condition for v, which is part of the analytical initial condition. And in fact, if we go a little bit further up here in this routine, we find that the name of this, this routine has, of course, initial conditions, analytical initial conditions for a whole bunch of other things, depending on what application you're running. But if you go at the very top of this routine, if we can get there, see there's a lot of them. Went maybe too much. Well, I'm just going to search initial. I just wanted to show you that this routine this block of code happens to be under this subroutine, which is analytical, which is the subroutine called when we do the initialization. But of course, this is a very long file, and you know, that's why you have these predefined places where you have to edit to help you out. So we did the initial condition for the u. Then this is for the velocity. Now there's another section that is the initial condition for the temperature. Here you see this. There's a nice loop here. Now the loop involves also the k direction, which is the vertical levels. In this case, all the temperature is initialized to a constant. And actually, if you look at this temperature array, which is we didn't do for the velocity, it has 1, 2, 3, 4, and 5 indices. The first 3 indices here stand for the I, which is the x direction, the j, which is the computational grid point in the y direction, k, which is the number of vertical layer that you're treating. Then this part here is the time step. And that's, in this case, you find that you're initializing 2 time steps, and that's because the time stepping scheme of the model has multi levels in time, and therefore you have to provide both of them. This was very similar to when we did the centered scheme within the MATLAB. So here what we do is we set the first time level to a constant t naught, which is just a constant temperature of some sort that is defined somewhere else, and then we also assign the second time step to be equal to the first, so we just initialize both at the same. Next, okay, so now we have another part of code that is where we define the surface boundary condition for the u momentum equation. And in this case, the surface boundary for the u momentum and also the v momentum is basically a mechanical stress applied at the surface of the model. And in this mechanical stress is actually the wind stress. And so the variable that we are initializing here is SUSTR. That stands for stress. No, sorry, this stands for surface u stress, and which is the wind stress. And here, so for the purpose of this application, we say that there's no stress, there's no winds that are blowing, and so we put a wind amplitude of 0, and we initialize the bottom boundary condition to be a 0 flux of momentum. So there's no stress. If you wanted to put something here, for example, to generate a wind-induced velocity, you would change the wind amplitude. The same is true now the surface boundary condition for the v momentum, and you have this loop, and again we're initializing the surface v stress to be a constant wind damp, which is 0 in this case. Next, now we have another initialization here. This is STFLX, and that stands for surface tracer flux, and this is the surface boundary condition for the tracer. And this particular is surface boundary condition for temperature. Okay, and so this is saying that there's a 0 flux of temperature at the surface. Okay, so there's no heat flux through the surface. Next, and again we have a similar variable called BT flux, and this is exactly like the one we just did, but it's the bottom T flux. And so we're just going to just put a comment here. This is the bottom boundary condition for temperature. Okay. In case you had a geothermal source of heat, this could be, at the bottom, then you could put this to equal to some analytical shape, for example. Or, as we will see in the future, these variables can also be defined through an input file, but in this case we don't have any input files. So at this point, the next occurrence of coriolis, we're back to the beginning where we configure the grid, and so we are basically done. Now you may ask yourself, how did you know where to put these things? Well, this is why we're learning together. In this case, you already know where you want to edit because you can follow the coriolis thing. In general, what you can do if you start from scratch is that you can copy an existing application like the coriolis and then start modifying that, and as you add pieces of physics, you can think about things that you may want to add. And we'll do more of this, in the progress of the class. So now I can quit this. Sorry, I want to save this. And once I've done this, then I am basically here again in the nonlinear code. I can go up 1, and I can go back to my application directory because I am done configuring this example. So all I need to do now is to run this, make sure that I didn't introduce any errors, and let's make sure it compiles before we quit this demo. And it seems like it's compiling fine. So as this is compiling in a different window, let's go back in the applications directory, and let's open this README file here. So to summarize, what we did is we first looked at this application cpp.defs.h file, and then we looked at the modparams.f file, and now we just looked at the nonlinear analytical.f. So using these three files, you can configure now an application like the Coriolis without touching anything else. So that's very good, and we'll stop the demo here. Let's just ensure that the code compiled. I think it was in this directory. Yes, it did compile fine, and so we are good to go.